So, in the last day we concluded by showing that any given non-smooth system, if you have a borderline like this and if you have a border crossing fixed point, then you obtain the eigenvalues here just before the border crossing and you obtain the eigenvalues there just after the border crossing, and then you can obtain the normal form from there, which is given as x n plus 1 y n plus 1. This is equal to this is for x n less than 0, and for x n greater than 0 this will just be substituted by the right hand side quantities. And I also said that the same result should also be possible to obtain the same result simply by a matrix manipulation of the Jacobian matrix obtained here and the Jacobian matrix obtained there. So, suppose you have obtained the Jacobian matrices like this. In this side, say you obtain the Jacobian matrices as say A1, A2, A3, A4. Okay. Then you want to obtain something like this. So, what do you have to do? If you transform the x vector x n y n as say initially it was say x bar and then you want to transform it to x. So, it should be say x n can be some matrix T times x n bar, where x n bar were the original ones. Now, this if the T is defined as 1 0 A 4 by A 3 and here it is the determinant divided by A 3, I suppose there will be minus, then you can easily see that using this transformation this matrix can be transformed into this matrix. So, in this case the trace is A 1 plus A 4 and the determinant is A 1 A 4 minus. Okay. So, this is another way of doing the same thing that we did. We can do the same thing using a different logic. So, finally, we are where we have obtained the normal form, and then using that we are trying to understand the behavior of non-smooth maps. Not the complete behavior, but we are exactly trying to understand the behavior of the non-smooth bifurcations, the border collision bifurcations. And the logic is that in the neighborhood of the border collision bifurcation, it suffices to consider the local linear neighborhood of the border crossing fixed point. And since the border crossing fixed point crosses like this, you are having to consider one side in the left, another side in the right, and the small box is then transformed and it is now written in that form, the normal form. So, where are we? We have obtained a changed state space description representing the local linear neighborhood where the border line is exactly the y axis and this is the x axis. So, this is not only the x axis and the y axis, this fellow is also the border line. Okay. In this part, yeah, it has got one description, in this part another description. As you have seen, it is the trace given in terms of the trace and the determinant of the left hand side, and this is given in terms of the trace and the determinant of the right hand side. We have also seen that one character of this map is that any point on the y axis maps to the x axis. So, all the points on the y axis would map to the points on the x axis. And where would 0 0 map? To itself. Okay. So, 0 0 will map to itself, and your y axis will map to the x axis. Now, notice when you say 0 0 will map to itself, this is not exactly correct because of this fellow, right. So, only when mu is 0, 0 0 will map to 0 0, that means the fixed point is exactly located at the origin, else not. When okay, we will have to find the location of the fixed point in this case. So, using the expression for the map, we can now obtain the locations of the fixed point. Now, you can easily do that, because your equation was, supposing we are considering the left hand side, then your x, okay, this is the equation. So, let us write it individually. N plus 1 is equal to tau L x n plus y n plus mu, and y n plus 1 is equal to minus delta L x n, that is all. Okay. How to find out the fixed point? You will say that x n plus 1 is equal to x n, y n plus 1 is equal to y n. If y n plus 1 is equal to y n, you can substitute it here. So, you can say x n is equal to tau L x n plus, I will substitute it here, minus delta L x n plus mu. So, from here you can obtain x n is equal to mu by 1 minus tau L plus delta L, right. How to obtain the y n? Simply by substituting it here, you get the y n. So, x star, this is of the left hand side, x l star, y l star is the fixed point, x l star, y l star is the fixed point as calculated from the left hand side equation. This equal to minus mu delta L divided by 1 minus, okay. It is not difficult to see that similarly you can obtain the quantities of the right hand side, that means you can calculate the fixed point that exists in the right hand side, and that would be given by, in absolutely similar way, x r star is equal to mu by 1 minus tau r plus delta r, and y r star is equal to minus mu delta r 1 minus tau r plus delta r, right. So, these two are the equations for the left hand side and the right hand side fixed points. Now, notice that this term and this term, they contain mu, they contain the trace and the determinant, and the trace and the determinant may have a positive value and the negative value, giving a positive value, negative value to the denominator. At the same time, mu can be positive or negative, and as a result the x l star could be positive or negative. Now, we have calculated this x l star using the left hand side equation, using the equations of this side. So, obviously, this value will exist so long as the x l star happens to be a negative number, that means this fixed point is in the left hand side. Else you run into a situation where you have calculated using the left hand side equation, the fellow does not exist in the left hand side. So, if this quantity is a positive number, the fixed point is actually here, but you have calculated using the equations of the left hand side. What do we infer then? We infer that this fellow does not exist, this fixed point does not exist. But notice, if your initial condition is here, then this initial condition and its further iterates will see that as a fixed point. Even if this fellow does not exist, it will see that fixed point, say it is here, it will see, and supposing this fixed point is the attracting fixed point, it will be attracted to that, and its dynamics will be guided by that. So, even though the fixed point does not exist, it has an influence on the dynamics, and therefore, we will call it a virtual fixed point. So, if it exists, means x L star this magnitude is negative, x L star y L star that fixed point exists, and we will call it a real fixed point, else it is a virtual fixed point. Similarly, when this x r star this quantity is positive, this fellow exists, it is real. If comes to be negative, then it is virtual. Clear? That is one important character of the map. The second important character is given by okay, here is a fixed point. Natural question is, will that be stable? And that stability is given by the eigenvalues of the fixed point, right? And for a map of this form, the eigenvalues can easily be written. Then the eigenvalues are lambda 1 comma 2 will be half tau plus minus root over tau square minus, where this tau and delta could be of either side, that is why I have not given the subscript. So, this is the expression for the eigenvalues, and when these eigenvalues are less than unity, this fellow is stable. If these eigenvalues are greater than unity, this fellow is unstable. Clear? So, one condition is when this plus thing, when this is substituted by the plus 1, only you take the larger one, that equals plus 1, that is one point where it can become unstable, or the other one, the lower one, when it becomes equal to minus 1, that it can become unstable, or if there is a pair of complex conjugate eigenvalues, and you can easily find out the condition when the eigenvalues will be complex conjugate. When? Yes. So, easily you can see that the complex conjugate eigenvalues happen when this is greater than this. So, tau square less than 4 delta. So, complex conjugate less than, or tau lies in between minus 2 root delta and plus 2 root delta, same thing. So, it becomes complex conjugate only when the relationship between the trace and the determinant is like so. Okay, let us now find out what is the condition for the real eigenvalues stability. Can you just work it out? Take the plus and make the whole thing equal to 1. Take the minus and make the whole thing equal to minus 1. Do it. Half tau plus root over tau square minus 4 delta is equal to 1 is the condition, is the critical condition. So, tau plus root over tau square minus 4 delta is equal to 2, right. So, root over tau square minus 4 delta is equal to tau minus 2. So, tau square minus 4 delta is equal to right. So, you get tau equal to fine. So, that is the critical condition, and the fixed point will be stable so long as tau is less than 1 plus delta, and it will be unstable if it is greater than 1 plus delta. Similarly, you can work it out for putting negative here, minus here, and equating it to -1, that is another instability condition. Can you do that and give me the condition? The other condition, so this is one instability, and the other is delta plus tau is equal to -1, but I would like to express it as tau as related to delta. So, it will be yes tau greater than minus and this is okay. One stability condition is this, instability condition is this. So, there are two conditions, right. So, I am talking about stability condition that happens when it is less than 1 plus delta and greater than -1 plus delta, then they are stable. Now, you know that the fixed points are classified depending on the character of the eigenvalues, and you know that if there is one eigenvalue, okay, let's just recapitulate that. Say I am drawing the complex plane and the position of the eigenvalues as related to the complex plane. This is the unit circle. What if you have two fixed points like this? What is it called? It is a regular attractor. So, this is a regular attractor. When will that happen? From what we have already derived, when will that happen? Regular attractor. Firstly, it should not satisfy the complexity condition, and secondly, it should be stable. So, the stability condition is that it will be between no 2 root delta, right. This is where it becomes complex and this is where it loses stability. In between should lie. Okay. Similarly, if you have when will that happen? Yes, minus 2, yes. This is this fixed point is called a focus, okay, and that happens when it is between -2 root delta when will this condition occur? What is it called? A fixed point outside the unit circle, a fixed point inside the unit circle, both real. It is a regular saddle. When will that happen? When one stability condition has been violated. Which one? This one. So, then this is similarly. Let me draw here so that we can finish within this page. What if this, or this can also be here, it is an attractor because it is inside the unit circle, but there is one eigenvalue negative, which means that there is a direction in which it flips. It is a flip attractor. Can is it visible? Yes. When will that happen? Flip attractor, that is Next, what is it called? There are okay, this could be here also. That means I am saying that one eigenvalue is outside the minus 1 point, that means it has gone out, and the other one could be this side or that side. Then it is called it is a flip saddle. And when will that happen? Yes, that is tau less than minus 1 plus delta. And here I am again not writing the subscripts because that pertain to both the sides. So, when we are talking about the left hand side fixed point, we will simply put L in the subscript. When we are talking about the right hand side fixed point, we will put a R in the subscript. But these are the basic types of fixed point that can be. Can it be like this? Is it possible? Yes, it is possible, but you would notice that the magnitude of the fixed point, magnitude of the eigenvalue, just obtain its magnitude, you will find it is nothing but delta. So, obtain is this fellow's magnitude, you will find this is nothing but delta. So, can you do that? Can you check? Yes, check. So, magnitude of this means you have to square and then simplify it. So, when the delta determinant is exactly 1, it should lie on the unit circle, but if it is less than 1, if the determinant is less than 1, it is actually a dissipative system and the eigenvalues will be inside, and if it is greater than 1, it will be outside. If it is greater than 1, it is a unstable focus where the orbit will be spiraling outwards, while if they are inside, it will be spiraling inwards. Okay. So, the fixed point that we are talking about, they could we have decided about their existence, when will they exist and when will they not, and we have also decided about the type. These are the types that are available. Now, you would notice that then depending on the relationship of the trace with the determinant, we can sort of tabulate the character of the fixed point. If this is the trace, then if it is between minus 2 root delta to plus 2 root delta, it has one character. What is it? What is it? Complex conjugate. If it is 1 plus delta, if it is between 2 root delta to 1 plus delta, it is a regular attractor. If it is outside that, a regular saddle. Another here is minus 1 plus delta. If it is within these two, it is a flip attractor. Outside this, flip saddle. Right. So, on the real line, I am now able to categorize these fixed points depending on the relationship with the trace with the determinant. Now, in this system, what happens? As you vary the parameter mu, notice that as you vary the parameter mu, where was the tau L was written here. Let us keep them side by side. If mu is negative, then this x L star, it has the fixed point's position is also negative, provided depending on the denominator, but in general you can consider that this fellow is positive. So, that mu is negative means this fellow is also negative, mu is positive means it becomes positive. So, which means that as the parameter is varied, you have a fixed point crossing like this, and at mu is equal to 0, it is on the origin. So, from this side it crosses the origin, it may not cross also, but nevertheless in general, in order to understand, you can say that at mu is equal to 0, the border collision occurs. I am not saying in the general sense, I am saying that mu with respect to, as related to this quantity, it will be either existing or not existing. So, always you cannot say that a fixed point comes and hits the border, but always you can say that the border collision happens at mu is equal to 0. Clear? That is definitely correct, because mu 0 means this fellow is 0. The fixed point is on the border, means it has hit the border. Fine. So, while it has not yet hit the border for mu less than 0, there is a fixed point, and its type, as we have already shown. After it has hit the border, there is a fixed point and its type. So, for mu less than 0, we can say that there is a type of the fixed point. For mu greater than 0, there is another type of the fixed point. A type of fixed point changes to another type of fixed point, right. How will we represent that? There is a nice way of representing that. We can say that I will make a parameter space of tau L, tau R. Tau L parameter space, and then I know that the tau L represents, or tau L as related to delta L represents the type of the fixed point while it is in the left hand side. So, we will say that I will now subdivide, and this is my 2 root delta, this is my minus 2 root delta, this is 1 plus delta, this is L, and here it is minus. So, the tau L as related to this, just like here. Similarly, tau R can be related to the determinant of the right hand side, which will be like this. So, we will say that I will divide like this also. And this is 2 root delta minus 2 root delta, this is minus 1 plus delta, these are all R. Okay. Clear? The moment we have said that, we have essentially said which type of fixed point gets converted to which other type as it moves across the border. So, a border collision means a type of fixed point hits the border and changes into some other type, and that we have essentially defined. For example, if say I place my point here, or this is not the, okay, you can do that, yes, here, what does it mean? What does it mean? It means that while it is in the left hand side, its eigenvalue satisfied the condition that the trace is between 2 root delta to 1 plus delta. If it is in 2 root delta to 1 plus delta, what is its type? It is a regular attractor. And when it crossed over to the right hand side, then its character is that its eigenvalues are such that the trace is below 1 plus delta, which means it is a flip saddle. So, you can then say that here is a situation where a regular attractor hits the border and changes into a flip saddle. So, just by placing a point in this parameter space, you are saying that, conveying that. So, this will represent our primary partitioning. If the parameter space is now partitioned depending on which type of fixed point gets converted to which other type. So, primary partitioning is pretty simple stuff. So, this is the primary partitioning. Now, you would realize that there is a similarity with what we did in 1D. Similarity in the sense there also we had in case of 1D the determinant is 0. The determinant is 0. So, imagine the determinant is slowly changed and it is approaching 0. What will happen to this parameter space? This will become 1, this will become -1. We have done exactly that, and what will happen to these two fellows? It will shrink to 0. So, as you have the determinant shrinking to 0, the range for which you have a spiral attractor, that also shrinks to 0 size. Ultimately, you do not have a spiraling behavior at all. Okay. So, the next job obviously is to consider what happens in this parameter space, every point of this parameter space. First, let us consider some trivial situations in order to get used to what will happen. Say, if I have initial condition somewhere here, what do you expect? Here a spiral attractor, because it was between -2 root delta plus 2 root delta, converts into a spiral attractor, because it is still within that. A spiral attractor remains a spiral attractor. In this part, in this part, it is a regular attractor that is converted into a spiral attractor, but either case it becomes an attractor. So, you can say that the behavior will be like this. So, this is the mu and this is the x, this is the bifurcation diagram. There you will only see a bend in the root of the orbit, you will see a bend, but nothing more. You are not expected to see much more, because both were stable. Yes, this is the simplest situation, and you can say that in this situation you have some people would like to say that there is no bifurcation. Some people would like to say, okay, let us call it a bifurcation. There was a bend and we need to define that. So, either way you can say that it is a situation where the stability status of the fixed point does not change. A similar situation will also occur, say here. What has happened here? Here it was a regular saddle that changes to regular saddle. I mean, it does not change. Here a flip saddle remains a flip saddle. So, in these three compartments, the stability status of the fixed point did not change, and while it was regular saddle it was unstable, while it is flip saddle it is unstable, and the unstable thing remains an unstable thing. So, you do not expect any periodic orbit to occur. So, it will actually go to infinity. Okay. So, these three are somewhat simple situations. So, I will mark them like this, and this whole block I will, should I mark or not, because I will need to do something about it later. Okay, just remember this also falls, this box also falls under the situation where the stability status of the fixed point did not change. But there will be complexities which I will come to later, not at this stage. First, let us understand the basic character of this. What happens here in this part? Can you work that out? What happens in this part? In this part means, what is the character? Your trace of the left hand side is greater than 1 plus delta L, and in the right hand side it is less than 1 plus delta R. Okay. Now, you already have the equations look at these equations of the positions of the fixed points. What do they tell you? Tau L greater than 1 plus delta L, tau L greater than 1 plus delta L means this term is negative. This term is negative means this fixed point, left fixed point will exist only if this fellow is positive. Okay. Now let us look at the right fixed point. Tau R was, let us look at it again. Yeah, tau R was less than 1 plus delta R, right. Tau R is less than 1 plus delta R means this fellow is positive, the denominator is positive. So this fixed point will exist so long as positive, which means that for mu negative none of these fixed points exist, and the fixed point exists, both the fixed points exist for mu positive. Okay. So this means that this is a situation where there is a birth of a pair of fixed points at mu is equal to 0. At the border collision, a pair of fixed points are born, and if you look at it from the other side, that means mu is being reduced from a positive value, then you would see a pair of fixed points approaching each other and then colliding at the origin of this state space and disappearing, vanishing. Now it is not true that you have never come across this situation, you have. In fact, in a smooth system, smooth map, you have come across this situation, no, where a pair of fixed points are born. Here also you have a situation like that. So it is actually the non-smooth analog of a saddle node bifurcation, is non-smooth analog of a saddle node bifurcation or a fold bifurcation. This is also called a non-smooth fold or non-smooth saddle node bifurcation. Okay. But the only difference is, as you have already noted while we are talking about the one dimensional system, is that in a smooth map one is unstable, the other must be stable. One fixed point is unstable, the other fixed point must be stable, because it is a smooth line, you cannot avoid it. While in this case there is a possibility that both could be unstable. Could both be stable? No, that is not possible, because you have taken tau L to be greater than 1 plus delta L, that is where you have doomed it. One is definitely unstable, but the other, yes, that could also be unstable. Obviously, if let us look at the fixed point of the right hand side, if the eigenvalues of the right hand side is such that the tau R is between 1 plus delta R and minus 1 plus delta R, then the fixed point there is stable. Okay. But here, where it is below minus 1 plus delta R, it is obviously unstable. So if you place the point here in the parameter space, it means that you have chosen a parameter condition for which there is a birth of a pair of fixed points, both of which are unstable, one a regular saddle, another a flip saddle. Okay. So a pair of unstable fixed points are born, one a regular saddle, another is fixed saddle. You have also seen in case of 1D map that under that condition, when both the fixed points are unstable, there is a possibility of existence of a chaotic orbit, right. You have seen that. Here also that can happen, but we will take a closer and more detailed look at that a little later. But let us now those details I will come to, as I have said that here are some details which I will come to later. There are some details also we will come to later, but let us realize what happens here. Here what happens is, you have on the bifurcation diagram, here is the mu axis and here is the x. What will you see? You will see the birth of a pair of fixed points, one of them is stable, the other unstable. Okay. That is what happens here in this part, and in this part you will expect something like this to happen. This is not a period 2 orbit, this is a pair of unstable orbits, out of which one is a regular saddle, the other is a flip saddle. Now, if there is a question of a regular saddle and a flip saddle, obviously we have to find out what other orbits can be existing. Is it possible that a period 2 orbit will exist? I would not say that is impossible. I would not say that is impossible. So, we will consider that condition later. Let us now come to this side here. Let us understand the primary partitioning first in clear terms. What happens here? Your trace of the left hand side is between minus 1 plus delta to plus 1 plus delta. Trace of the left hand side between these two means that before colliding with the fixed point it was stable. After colliding with the fixed point, what happened to it? It became r, and it is less than minus 1 plus delta r, means it became a flip saddle. So, you can subdivide this. If you place the point here, you can say that a regular a spiral attractor gets converted into a flip saddle. Here a regular attractor gets converted into a flip saddle, a flip attractor gets converted into a flip saddle, but either case an attractor gets converted into a saddle. In that case, what will happen? So, I can expect there the behavior is something like this. In the bifurcation diagram, a fixed point comes, hits the border and becomes saddle. So, what happens then? Obviously, the question is what happens then? Will there be any stable orbit? Well, whenever this kind of thing happens, do notice that this is similar to the situation in the smooth map, where you had the fixed point that lost stability, and as it lost stability you had a period 2 orbit being born. So, the obvious line of thought would be that okay, here I find that it is losing stability, here as it lost stability it became what? A flip saddle. In case of a smooth system it became a flip saddle, here also it is becoming a flip saddle. So, the natural line of thought would be okay, let us check if the period 2 orbit will exist, right. How will you check if the period 2 orbit will exist? How will you check? Simple, you have got the real line, this is the 0, period 2 orbit means something like this. So, start from a point in the left, apply the left hand map, come to the right, apply the right hand map, come to the left, and then equate x n to x n plus 2, y n to y n plus 2. Okay. And then you get an algebraic equation solving which you should get the position of the fixed point. Clear? That is reasonably simple affair, should be a reasonably simple affair. I will not trouble you right now with the task of actually deriving it, but you can see that it can be very easily derived. Again, what will you do? You will start from here, assume that x n y n are here in the left hand side, apply this, obtain x n plus 1 y n plus 1, and then it has come here. So, you will have to apply the right hand map, which will be these two subscripts replaced by r, apply it again, come back here, x n, you have obtained x n plus 2 y n plus 2, and then equate that, you get a algebraic equation. If you solve, you will get x 2 l star the one that is in the left hand side, x 2, that means it is a fixed point of the second iterate map. It comes to minus mu 1 plus tau r plus delta r by tau L tau r minus 1 plus delta r and the other one x 2 r star is equal to minus mu, this should be by symmetry, because if you start from here, come here and come back here, what you get? If you start from here, come here and come back here, you should get the same thing, only with r's replaced by l's and l's replaced by r's. So, I can blindly write 1 plus tau L plus delta L tau L tau r minus 1 plus delta L okay. The denominators are the same, only the numerators are different. Now, I said that the question that I am addressing now is, when this fellow has become unstable, will the period 2 orbit exist? What is your answer? By looking at this, notice, in order for the period 2 orbit to exist, this term should be negative and this term should be positive. Here, mu, let us first consider mu. I am now considering mu to be positive, If mu is positive, then the existence will depend on this, and I am considering the situation where is my parameter space? I am considering the situation, okay, let me write here, okay, I am considering the situation here, which means my tau L is between minus 1 plus delta L to and tau r is less than minus. On this basis, take your decision. Will this fixed point exist, this period 2 fixed point, or not? What is your answer? It will exist or it will not? It will not exist. Okay, let's clarify your argument. Let's look at the situation here, tau r, which appears here. So, tau r less than minus 1 plus delta r. So, take it to this side, you have negative, this term negative, right, this term is negative and this term is negative, and then this fellow will be, I want this to be negative, and this term is negative, here is a minus. So, it will be existing for think also there is this term, right. So, here is this term and this term, we have made a hard conclusion because of this term is negative, this term times this minus is all positive. So, forget about this. Then ultimately your decision should depend on the relative magnitude of mu and this, yeah. Now this we do not know yet, but we have concluded that the existence will depend on mu and this in such a way that this division mu by this should be negative. Okay. Clear? Now let us look at the stability condition of this period 2 orbit. What is stability condition? When will this period 2 orbit be stable? You have to talk about its eigenvalue, right? And how would you obtain its eigenvalue? By multiplying these two matrices. You multiply these two and obtain its eigenvalues, right? Now, if you do that, then the eigenvalues come to be, let me again not trouble you with the nitty gritty details. The eigenvalues of the second iterate are half tau L tau R minus delta R minus delta L plus minus root over tau L square tau R square minus twice tau L tau R delta R minus twice tau L tau R delta L plus delta R square plus delta L square minus twice you might say that this is too big, too complicated, right? Well, it is not. This is easily manipulable, and so I would not say that this is a unhandleable situation. I would not say. I will give you the task. Find out when this thing will have this is the eigenvalue, right? The stability condition is that it has to either be plus 1 or minus 1. So, equate it to plus 1 and simplify this hell of a lot of business. You will find that can be done in just 2 steps to obtain a very simple expression. Similarly, for this equal to minus 1. Okay. So, here we are talking about real matrices with real numbers. So, the period 2 orbit will be unstable in these 2 ways. Can the period 2 orbit become unstable as a complex conjugate? No. So long as you are considering the determinant to be less than 1, meaning you are considering a dissipative system, the determinant in the 2 sides multiplied together will also give you a determinant that is less than 1, and therefore, that cannot go out. So, going out like that is out of question here. So, these 2 possibilities we have to consider, that it can either become equal to plus 1 or it can become equal to minus 1. So, before you come to the next class, you just work out yourself that from this expression what will be the condition for which, notice this and clarify your logic, that here is 3 terms really, one term mu, another term here, another term here, here also mu, this, and the stability will depend on something, but the existence will depend on their relative magnitudes. So, ultimately their magnitude should be such that this value is negative and this value is positive, then only it will exist. So, that decision you take. I leave you to take that decision on the basis of your own logic, but here is a clue, this is the eigenvalue and you can work it out yourself. Can you see that? This will get simplified out, check that out. Okay, I'll stop now and we will continue with the next class, where we will go on to further partitioning of this parameter space to see what other possibilities exist in this case.